organism, it would be impossible to synthesize that compound in a lab. Like, what made you living was that the stuff inside you was special in some way, and those were organic molecules, and what made that table inorganic and dead was that it was made up of, you know, a totally different subset of stuff. Then some guy made urea, and like everything went to heck because you make urea and they make urea and everyone can be, and here we are saying we don't have a great definition anymore for what organic chemistry is. So we have kind of a working definition. So never on an IB test is going to say define organic chemistry, but if you want a working definition, it's stuff with carbon at its backbone. From my perspective, carbon dioxide is pretty inorganic. I can imagine a lot of, like, I'm going to mix acid with limestone and I'm going to make carbon dioxide. I don't really think of that as the process of cellular respiration happening in my body making carbon dioxide. It's very much on that line of is it organic or inorganic, and fundamentally, who cares? We don't. The reason that this is a special area of chemistry still, even though this definition doesn't really make a whole lot of sense, is just the amazing number of compounds that we describe as having carbon at their core, or carbon at the backbone. I wrote down the number because I wanted to dazzle you. There are 90,000 known inorganic compounds. There are well over 1 million known organic compounds. So it's more than a factor of 10, and I would have guessed it was a factor of 100. So we're going to limit ourselves to focus on a single element and find that there are a whole lot more compounds of it. And it's because carbon has this cool ability to catenate. And so computer scientists Hispanophones, catena.
Is it connecting like?
No, I mean it is, but that's not what it means.
Like a series of things.
It means bridge, I thought. No one speaks Spanish. Okay, we'll get the other class. We need Mauricio, we need Nicole. And so lots of carbon-containing compounds will have a backbone or a core that looks a bit like that, with carbons really efficiently bonding to each other. It can do it twice, or once, or 3 times, or 4 times. Can't do it 5 times. Carbon always makes 4 bonds. And it's so always that we frequently don't draw all the bonds because everybody knows that carbon's going to make 4. So if I didn't show you a bond, what do you assume is there? Hydrogen is the right answer, everyone. We assume it's hydrogen. So if we don't tell you what it is, we assume it's hydrogen. Now, would Chloe get marks on an IB test if she wrote this down? No. Your teacher can be as lazy as she wants to be. Y'all have met me. It gets cumbersome to write a lot of hydrogen sometimes in your notes. I appreciate that fact. But I know on an exam, and I know on an exam key, that I'm just going to take the extra time and fill in this. So I tried to show you this. And this is gross and hard to write and messy, and yeah, I did my best. But that there is known as a structural formula. It's a structural formula because I have shown you the bonding. I've shown you how all of the carbons are organized. Have I shown it to you in 3-dimensional space, Mohab? He's very interested in something or asleep, I don't know which. Oh, very interested in his notes. I don't know, he just kind of asleep. You're a good kid. Is this a 3-dimensional structure? No. So Lewis structures kind of fail us, because Lewis structures try to show a 3-dimensional molecule with 90-degree bonds on a flat surface. What is the actual structure around any of these carbons? Emma studied that. What? Close, but not it. What's the structure around a central carbon atom? The structure, I don't know the answer to that question. How is the carbon hybridized, Amarashi? Or what is the Vesper shape associated with any one of the carbons? Or the two maybe? Tetrahedral? Tetrahedral, take that. So this carbon has 4 electron domains. So y'all are gonna tell me it's tetrahedral. Y'all are gonna tell me that the bond angles are 109.5 degrees. Right?
Audrey? Yeah, what?
Am I lying yet?
No.
How's it hybridized?
SP3.
I promise it's just counting.
So this structure is a bit of a simplification. It calls out the connectivity, but it hides what it looks like in 3-dimensional space. So again, we have a word for this, we call this a structural formula. This has more information than if I told you that this was C7H16. I think I counted right, but all you can count. C7H16 would be the molecular formula. The molecular formula doesn't tell me, hey, that carbon in the middle has 2 things hanging off of it. If I just said, I have C7H16, Ethan Morgan would have drawn something easy. That molecule has the same molecular formula, but it has a different structural formula. I drew the 16 lines that would attach it to the 16 hydrogens, but again, I get to be lazy. I'm not answering anything. I don't think I learned anything from drawing those H's. So a structural formula gives us the connectivity, and we will refer to these 2 things with the same molecular formula, but different structural formulas as structural isomers. These 2 things are isomers. It should be C7H16. 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 8, 11, 13, 16. 3, 5, 7, 9, 11, 13, 16. That's okay.
So essentially structural isomer is having the same molecular formula but different structural formula.
Yes, and I'll use the word connectivity. So connectivity, like the different atoms will be bonded to each other. So if you think ahead to your biology chops, you know that you have cis fats and trans fats.
Yeah.
I will call those isomers of each other, but they have the same connectivity. They have a different shape in space, so I'll have a different word for that. Or if you look at, where would you know an isomer from? You think of any D and L that normal people would know? Okay, we're not there.
Okay, so isomer is different molecular formula, is same molecular formula, different molecular structure.
Structural isomer is same molecular formula, different structural formula, or different connectivity. I would take both of those.
Also, how do we know it was sp3?
Because anything that has 4 attached is sp3. Remember the sum of these exponents? So S has the 1 we don't write because we're math geniuses, and the 3, so 1 and 3 is 4. That tells me how many things you're connected to. Good times?
Is everything hybridized?
Yes. I'm almost, but yes.
Sometimes like in the molecular formula, like I see people like instead of doing like the C7H16, they do like CH3, CH3. What is that?
Okay, so Audrey has come across another way we write these. So this is called the full structural formula, or the complete structural formula. But can you imagine having a typewriter and trying to put that in a book and how awful it would have been? So to like organize the H's and stuff. And so we've come up with what we call a condensed structural formula. In a condensed structural formula, we go along the main chain and we write down the carbon. So I'm looking at that leftmost carbon and the hydrogens that are attached to it. You can draw the hyphen or not. The instructions that are on Canvas tell you to draw the hyphen. I think the IB textbook typically doesn't have the hyphen. This is something that Melania has to read. It is not something she has to generate. Clear? So I don't care if you put the hyphen in or not.
That's the condensed.
This is called the condensed structural formula. So again, the instructions that I have on Canvas tell you to draw the hyphens or dashes between the carbons along that main chain. So this carbon is bonded to 3 hydrogens. That's this one right here, 1, 2, and 3. This carbon is bonded to 2 hydrogens. So I've shown you that. The next one actually has carbons attached. And so without a whole lot of, expectation, I just showed you what was attached. I have looked relatively hard for a clear set of instructions about how to map from the left picture to the right picture, and I've never found something that I thought was necessarily worthy of your time. So I think in a Canvas assignment you might have, I don't know, could be there after class, we'll see. It's gonna link to an article that talks about this, but I also know it's not a skill you need to perfect. So again, you need to be able to read this, and it seems just to get really complicated. The IB focuses on molecules that have 6 or fewer carbons, and typically no more than 2 and often just 1 functional group or piece of interest in the molecule. This molecule legitimately has nothing interesting in it yet. We're gonna work on that over the next several days. When you take organic and Amarachi is questioning her health science future, she's gonna have to do some naming that gets hard. We're not gonna do, it's gonna be plenty, and you're gonna feel like it's plenty. I promise that you're gonna not wish it were worse, but there is a next level, and we just don't have to know it. And most of the materials are there for a college level organic class that's gonna spend a full year learning what you're gonna learn in the next couple weeks. And so you can't be a master of everything. You can't do it. You're not gonna learn a year worth of content before you may or may not go on trips in November, before you may or may not finish your IA, right? It's just not reasonable. So I tried really hard to collect materials that didn't go too far overboard. And I have tried for many years to do this because it's really easy to go off the deep end. There is one more structural representation that is increasingly being used in IB, and it's known as the skeletal formula. In 2016, if Emma wrote down her answer as a skeletal formula, she would have received 0 marks. It is not officially in the syllabus, and it is not something that it seems like I should be teaching you. However, watching the exams evolve over time, an increasing number of the questions are using this format. Any self-respecting organic chemistry book uses this format. So this is also in the Melania probably has to be able to read this, but she probably doesn't have to generate it. The way this looks is I'm only gonna draw the bonds between carbon atoms. So coming along here, I have 1, 2, 3, 4, 5 carbons in the line, and 5 carbons is gonna come with 4 bonds. I can count to 4. 1, 2, 3, 4. And the carbon in the middle has 2 more carbon bonds. And so that is the skeletal formula of our molecule. Yeah, that's it. That's all we write. We only draw the carbon-carbon bonds. So every line represents a carbon-carbon bond. Every vertex represents a carbon with enough hydrogens to make sure it's bonded to 4 things.
So if there was only 1 carbon coming off of this intern, then you would just have 1 line.
Can you explain that again?
We can try.
It's like how, in bio, you see it used to as fats a lot. Fats are just those squiggly lines.
Yes.
It's the same thing.
So I'm gonna do this for this one as well and try to explain it again, and then we'll come up with something more interesting when Reggie's done. So this carbon right here is the carbon that's bonded to 4 other carbons. And these are the 4 other carbons. So this carbon is the special one, and it's bonded. Okay. This carbon is the special one, and it's bonded to 4 other carbons. Yes.
Does this only work when the carbon is bound to hydrogen, or this also work for any other element?
So the only thing that you don't show is hydrogen.
Oh, okay.
So the hydrogens are understood, but if you wanted to draw butanol, you would draw that. So you can see that this carbon is bonded to another carbon, because I didn't write it. It's double bonded to an oxygen, and you've counted to 3 things, and so you might know or not know that there's a hydrogen there. And if Margaret's really intent on what this hydrogen is doing, she'll draw it. But if she don't much care, she doesn't have to, because the hydrogens are understood. If you drew a sugar, can't even draw a sugar anymore. Okay. You would probably draw glucose like this. I think what Elizabeth was saying is you saw this same structure in your biology textbook. That's a carbon, and you're drawing the carbon-carbon bonds, but you're showing the other ones. In this projection, we do show the hydrogens because we care if it's alpha glucose or beta glucose or whatever. Melania.
So the lines are the bonds?
The lines are the carbon-carbon single bonds.
And then the points are the carbon?
Yes, the vertices are the carbon atoms. Well said.
If it was just that, do you have to make the circles, or do we just leave it?
No, I was just trying to point out where in the structure we were getting these.
Do you guys remember the 3-dimensional structure balls that you may have seen? Like, oh, here's a little carbon ball, and you stick a little thing in it. It goes over here to another carbon ball. You've seen those before? That's exactly what that is. Oh, look. Little carbon balls.
I got them out to do things. It's just time goes so fast and so slow every day.
So how would you describe this? What would you describe as being the representation of just the carbon bonds?
Well, it's of the whole thing, but like you're explicitly seeing the carbon bonds because that's all we've got so far.
Wait, so like the one with like the O that you proved there, is it butanol or
That's butanol.
butanol?
Yeah, I try to really say the al hard because it's an aldehyde. And then we proved that I don't speak Mandarin, and I try to tell you what the stinky, how do you say smelly or bad smelling in Mandarin? That sounds something like cho.
In Cantonese, it's now. So it's
What's the what? This one? Just making sure it's coming up, okay? So Emma wanted to practice going backwards, so she counted 1, 2, 3, 4 vertices. So she knew that there were 4 carbons. Now here, she needs 3 more bonds to hydrogen because that carbon always has to have 4 bonds. Here she needs 2, here she needs 2, and here she needs 1. So that's 1, 2, 3, 4, 5, 6, 7, 8 hydrogens and 1 oxygen. So this would be the molecular formula, that would be the skeletal structure, and perhaps a better way and the way that we will represent this most of the time is with a nice full structural formula. So I will draw this a lot of the time. We'll go with 80+% of the time. Like I will be drawing full Lewis-ish structures. I don't always show bonds to hydrogen as bonds. Like it's a little bit of a lazy thing. We don't normally draw lone pairs when we're drawing some organic molecules. It's not a true Lewis structure. I'm going to try to show you the full structural thing. Just want you to be aware that this other structure exists, and we'll practice reading it. The MOHEB is never going to have a draw the skeletal formula day.
There's no skeletal formula for methane.
Right, you cannot draw, like officially it would be a dot, and so we just draw the full structure. So if you had to draw this for methane, you would draw it like this, because there isn't really a better option. For ethane, you can draw that. But the dot just doesn't feel good. Amarachi.
So to clarify, like, a point at the beginning of the line, is it the carbon atom or is it the bond?
The point, the vertex, or the end of a line is a carbon atom. The line I draw is a carbon bond.
So for example, in that shape, the first like this shape, this point here is a
That's
bond.
the very beginning is a C.
So each of like the points have like a C on it, right?
So a corner or a vertex.
Yes. So now I've tried to draw the atoms in without making too stupid of a mistake.
So is it always gonna be the shape of that like different from that? Because that one, the special C that we identified, I guess, around it, it's like a cross shape.
Yes.
So it's always gonna be.
Yeah, almost always. You have some ability to make it better.
So these two.
Yes. There's never, like, increasingly there are questions that use this form, so I feel like I have to show it to you every now and then, but never have they asked you the question. Yeah, and it's manageable. Like, they give you some hints in the problem, but just, we went from absolutely never use it to it's now allowed if Margaret answers this way to accept her answer. But I don't recommend it unless you get really good at it. But yes, and so one of the issues is that if you guys find resources online, if you're the dorky Melania and you're going online to be like, oh, I need to study more organic, you are quickly gonna get to the point where everything is in skeletal formula. You are quickly gonna get to a point where things have more than 6 carbons and more than 1 functional group. So beware. You're allowed to learn as much as you wanna learn, but don't forget that you have a fun English class to practice for too. So,
Oh my gosh.
I liked where Amarachi, I think, was going with the shape of the skeletal structure. Do you start to get that sense of a 109.5 of a tetrahedron? A little bit, at least? It's not straight, it's not 90 degrees, it's not perfect, but at least I'm indicating like a little bit of that bond angle being correct. So here, I could believe that this is part of a tetrahedron, and if I were cool, I might be able to show you where those other hydrogens are. Right? And so you do usually draw this as an X, as she pointed out, but it wouldn't be too hard for me to 3Dify this. And make these 2 methyls. And so one of the positives of a skeletal formula is that it starts to get you a little bit closer to 3-dimensional shape. It's imperfect, but it hints at it. Here too, I'm trying to make it clear what a sugar looks like, so I'm not trying to give you 3-dimensional shape. I'm trying to point out what I think is interesting. Is this OH up or down? Is this about to make some amylose or some cellulose? I don't know how much y'all know about it, biologists. Margaret and I were just...
Amylose, I just know it was a question like everyone missed on. Like
Oh,
amylose
yeah, it was
is
like-
amylopectin.
What about amylopectin?
We have the difference in structures.
What
Like,
is
like,
amylopectin?
one of them is cellular, one is like.
The 1,4 versus 1,6 linkage.
Yeah. We all missed that.
You passed the
Let's
It
go.
was such a tiny detail that you wouldn't think would be on there, but it just kept popping up every single time we had section on what was it? Lipids?
Carbs.
Carbs. It was when we had to do all of them together. Everybody, when I say everybody missed it, every single time, everybody missed it.
There's so much. There's so much. Okay.
Now, was that second image butane or butane?
I haven't named anything on purpose. Nothing's been named. Oh, I called this butanal. I called this butanal.
Don't write that down. You don't need to write it down.
I will get there. I chose this because, like, one group that was obviously mostly male children, saw this as butt, saw this as anal, and so they drew this molecule on like everything for the rest of the semester. So like this is the molecule that comes to mind because like that wall was covered with butanol. Children, you know? I was trying not to name things too much.
She literally made that.
No, I didn't.
You were there already, were you? You have a little bite next to this one? Okay, you guys have already talked about this molecule. It is an alkane. An alkane is defined in two ways. Probably the easiest way is a formula. It says if you have n carbons, you have 2n plus 2 hydrogens. So here I have 1 carbon. N is equal to 1. 2 times 1 plus 2 more is 4. So that is the smallest possible alkane. Another way of describing it is a carbon and hydrogen containing molecule with only single bonds. Quinn might refer to this as saturated. I think he had a test on lipids where he may have talked about unsaturated as well.
It's like the straight spool versus like the X spools because they can't stack or something. Is that bad?
That's cis and trans with the stack.
Can you explain this? And it's gonna like, it's gonna
So saturated is just a fancy word we use. That means you don't have any double bonds. It means that you couldn't put any more hydrogen in there. So if you look at this, you only have single bonds.
So you just see that, so like that's how you define it. Is if you see them.
You got it.
So number 2 is just know the overall.
But it has no functional group?
All the way to J.
Sure.
Yeah. Where you go? In that, like the little room for that.
Oh, okay, so that's.
If we increase the number of carbons by 1, we're going to have the molecular formula C2. 2 times 2 is 4, plus 2 more is 6. And this molecule is known as ethane. Can you imagine what this looks like as a 3-dimensional molecule?
They would have all 3 coming off of it on each side.
Okay. So I can envision that. I can try to draw it.
These are both alkanes?
These are both alkanes. So the gentleman over here was saying that they imagined the 2 carbons in a line, and then there were 3 coming off this way and 3 coming off that way. Can you see the tetrahedron? I hope so. We tried. Art is not my first ability. What do you think this wedge means? Means it is coming out toward you. So this hydrogen is drawn on my page, but it's actually coming out and pointing up at that light. The dash is behind the plane of my paper, so it's actually out in the hallway, but also up. The line is in the plane of the board. So this is known as wedge dash notation. That's the wedge, that's the dash. When we find out that a DT likes to draw more than I do, she can color in the wedge or not. It's her choice. I do an open because it's just too much for me. Lots of textbooks do a closed because ink is cheap. I mean, it looks better, but on the board I think this looks better. It's your call. What would this look like if you put your eyeball down here?
Looks like someone trying to grab you.
Maybe a bit like that. This would be a carbon. There would be 3 hydrogens making a triangle kind of shape, 2 of them up, 1 of them down. Then there'd be another carbon behind. It would have 2 hydrogens up and 1 of them down. We refer to that position as eclipsed. Because the 2 hydrogens here and the 2 hydrogens here are exactly at the same places on a clock with regard to the eyeball. Can you imagine other conformations?
Confirmations?
Yeah, I used a word I happen to find on our sheet.
Ways of viewing it.
Is there anything that forces the hydrogens here to look like the hydrogens there? Are they in communication at all? We have a single bond here. A single bond is going to be head-to-head overlap, 2 sp3 orbitals. It allows free rotation. So when we said that there were 3 hydrogens this way and 3 hydrogens this way, like they just used their hands, I made some assumptions, it would have been just as easy to draw a structure that looked like this. Or anything in between those 2 pictures. Those are just the 2 I'm capable of drawing. I need one in the plane of the board because I'm not very good at this.
So we're asking why is it symmetrical?
It's not. I'm saying that the 2 that you and I are most likely to draw are this one that I've erased and this one. That is sort of the opposite case where the hydrogens are exactly out of phase with each other. We call this staggered. Eclipsed, right on top of each other. Staggered, trying to avoid each other. For this, there's not a big energy difference. For this, we believe rotation is free. You can draw like a little potential energy diagram, and you might find like a nice sinusoidal thing if you're looking for a math IA. There you go. You can plot your sinusoidal function, and then you can put a chlorine here and see if that matters. And then you can put another chlorine here and see if suddenly these 2 chlorines next to each other are like, ooh, they really hate being near each other. They really love being opposite each other. Can you change that? Can you model that? Whatever. We don't go there. If you're looking for a sinusoidal function in a chemistry class, though, I found you one. Staggered and eclipsed. They are called conformations. When we take dogs to the American Kennel Show, we talk about the conformation of the dog. They're all like dog shapes, but we talk about like how they're standing there just perfectly. Their back is truly straight, they're slanted at just the right angle for a German Shepherd dog conformation. It's got an O, it's not like you're gonna be a Catholic, you're not being confirmed, you're conforming to a structure. Deep cut there, Elizabeth, deep cut. Okay, that's 2 carbons. What would happen if I had 3 carbons? I would. You know what this one's called? This is propane. Where would I find propane in my house?
Gas stove.
That's right. It's a gas. We use it a lot in cooking. Do we use it as a compressed gas in a barbecue, perhaps? The first 3 alkanes are gases. The 4th one, that's going to be C4H10. Is a liquid. I would find this in a lighter. So when you guys started IB chemistry last year, you guys used lighters and you used the liquid lighter to fill a 100 milliliter graduated cylinder, excluding the water from it, determining the molar mass of butane. These 3 beginnings, meth, eth, prop, and bute, are awful. must remember them. There's nothing.
Is there like
Remember that that's how much it's gonna be.
like and 9 or
6.
6? Okay.
Becomes trivial, like, if I only had to know 5 through 20, I think I'd be happier with the world, you know? Like the meth comes from Greek for wood because it's an alcohol that we distill from wood. So some people call methyl alcohol, which is like sterno, wood alcohol or grain alcohol. It's poisonous, it makes you blind. Don't do that. But after those first ones that are just about impossible to remember, the world becomes a beautiful place. And we start using the Greek prefixes that you would use if you were describing a polygon. So once we make it to 5, just like you call a 5-sided shape a pentagon, I'm going to call my molecule pentane. 6, hexagon, hexane. 7, heptagon, heptane. When you go to the gas station and you're looking for the octane number of your gas, you're looking for something about how the 8 carbon species behaves.
So are these prefixes the same for everything else from the first 4, or are they changing for just other things that are common?
They are going to be consistent through all of organic. If you have 4 carbons in a row, you need to know it's a bute.
Okay.
So I really wasn't super good at this, as I mentioned. And I like a good mnemonic when I struggle. And so the Teenage Mutant Ninja Turtles were part of my high school career, and so I went to college and I had to learn this. And so Michelangelo eats pizza by the pound. It's not great, but again, once you get to pentane, things are good. If Mohab has a moment and he calls heptane septane, we're all gonna know exactly what he's talking about, right? It's not a problem. We don't expect to name anything bigger than 6, so we're not worried about it, but we can make good, educated guesses, but like not knowing prop from bute is gonna be terrible. So let's all practice. Prop is 3 and bute is 4. That's opposite the number of letters?
Yeah.
Yeah. And honestly, whatever it takes, like, it's a stupid, like, I have to remember this. One more minute.
That's 4 C's, but it's butene 3, but PRL.
Right. You can now name straight chain alkanes. I wanted you to name this because we drew it earlier. You're gonna look for the longest chain, it's a pentane, and you're gonna tell me there are decorations on it. So next class, we're gonna learn to call this dimethylpentane. And we're gonna shove a 3,3 in there just for good measure. So our focus for next class is to go from, I can identify that the longest chain is 5, it's pentane, to saying what kind of decorations. There's nothing to worry about, like, it's very doable. 1, 2, 3. It's a position 3, and there are 2 of them, so I tell you the position of both. So this is a 1 carbon, so a meth at position 3. This is a 1 carbon, a meth at position 3. So at position 3, I have 2 methyls.